So I see a lot of excitement with this new topic, power setup. It took me a few years, like about 5 years to figure it out. And I come to this stage, and we expect you to learn it in a few hours. So it's interesting. I expect you to have a lot of questions about this topic. It's new. I talked with the Wyoming DOT. They know that this happened, but they do not have that technology and knowledge and information to able to take advantage of it. But that Iowa DOT seems like the first one to adopt and incorporate it into the design. So it's a good news beside the Hurricane Sandy we have a few days ago in Iowa. Not in Iowa, but the good news in Iowa with the power setup included in the design. Good and bad, but in the school that we help the student learning a new topic by giving a homework, exam, and quiz, but we do not have exam in this workshop. All right, to help you understand the topic. So this following presentation is to help you to recognize the difference. If you were to choose one of the construction control, we're debating whether you would choose WIP or you were to choose the Iowa DOT ENR formula. Right? I want you to upfront and let you know the differences based on the same problem, same construction, hammers and information by showing this presentation and recognize the differences between the two construction control methods in the LRTF design. So the goal of this presentation is to recognize the different design and construction control procedure in the track 1 described by Dawn and track 2 described by me before the lunch, and compare the different outcomes from track 1 and track 2, and recognize. I don't want to push that you should use WIP, but recognize the advantages of using WIP as a construction control by showing this example. So again, the step is pretty much the same. You have 10 steps in design and 2 steps in construction. This example is integrated abutment, H-pile in cohesive soil with setup, but then we have WIP and the modified Iowa ENR as the construction control for comparison purposes. This is the same problem that Don described and used in the track 1, 120 feet single span pre-stressed concrete, 0 skill, integral abutment, no brief boreholes, no special design consideration, and the elevation of the footing is at 433 feet. I will go through this rather quickly because it's the same as in the track 1. You have 6 feet of soft silty clay, 9 feet of silty sand, and the rest is with firm glacier clay. And this is the arrangement of the pile, 9 piles in a group, 10 by 57 friction pile. The factor load is 128 kips per pile, no down drag, no scour, or no uplift in the consideration. Construction control, track 1 using WIP, track 2 using the modified Iowa ENR formula, but no planned retap. Right? Retap is not planned. It's not required in this comparison or in this example. No need for special analysis or account for lateral load. So this is again the same table showed in track 1. You have the thickness of each layer, and then you have the N value, and then again you have the unit site friction that you selected from the Iowa design chart. Now I have 2 columns. The left show the result factors for design. Right? I want to emphasize that the selected result factors to estimate pile length using the Iowa Blue Book. Right? But we need to specify the type of construction control upfront during the design, whether you use WIP or the Iowa ENR formula. So if you were to specify WIP as your construction control, these are the resilience factors depending on the soil type along the pile length. All right? If you were to use the ENR formula, and these are the resistance factors depending on the soil type. And you can see that the resistance factors for WIP, right, as a construction control, is higher than the resistance factors for construction control using ENR formula, right? So what it means is that you get a benefit of using WIP because it gives you the higher resistance factors. It's shown in this following slides that the calculated nominal power resistance basically is to take the factor load divided by the resistance factors. And in this example, 197 kips is the nominal geotechnical resistance based on our Blue Book method and WIP as a construction control, as compared with Blue Book as a design method and ENR as a construction control, you require 213 kips. See the big difference between these two? So track 1 requires a smaller RN, nominal resistance, and that will be reflected in terms of the contract length. Right? As you calculate the contract length, based on these two numbers, one is 197, and this is 213 for this ENR formula. And the contract length for this track 1 is 75 feet, whereas the ENR formula requires you to have an additional 5 feet of total contract length of 80 feet. Okay, so the track 1 requires a shorter contract length by 5 feet per pound. That's the benefit of using WIP versus the ENR formula. So you have determined the contract length. The next important step is to determine the target driving resistance. That's where you realize the importance and the significance of using WIP plus setup versus ENR, right? So let's look at the calculation. If we were to use the WIP, we have two components, one for the anode driving component and one for the setup component. And this is the equation to calculate the target driving resistance. So you have a factor load divided this whole thing, and you figure out the setup factors at 7 days. Right? We suggest that we account for setup for up to 7 days. The reason for that is most of the historical data that we collect, most of the load tests was carried out during, in average, between 5 to 7 days. And 7 days was chosen. We think that is a time that is sufficient for you to construct the foundation before the superstructure or the total load is applied on the pile, and allow time for the setup to be developed over this short period of time of 7 days, instead of accounting for a setup up to a month or 2 months or 3 months. So 7 days was recommended, and that is the factors that correspond to 7 days. And we determine the the target driving resistance, and 166 is the number. If we were to use ENR formula, the target driving resistance is 233. Okay, now if you were to drive the pile, which one do you think that you would like to use?
You're the contractor, you're saying.
Think about that.
Yeah.
Right, you want to achieve the performance of the pile at a lower target driving resistance by taking the advantages of the setup and the benefit of the WIP analysis. So if you drive the pile that monitor using the WIP, that you expect to reach a lower target driving resistance as compared with a higher target resistance using ENR formula. Okay. So again, if you were to retap the pile, okay, what will be the target driving resistance at 1 day, 3 days, or 7 days? If it was use the whip, and the numbers is 197 kips as compared with 233 kips per pound using ENR. So lower target resistance at end of driving, lower target resistance during retap. All right, if we use whip as the construction control. So basically this to compare the different design nodes. All right, the contract length will be shown 75 feet as opposed to 80 feet. Resistance factors used 0.65 and 0.6 for ENR, and then a much higher resistance factors for construction control, 0.77 as compared with 0.55 using ENR formula. As well as the driving nodes, you required 166 as the target driving resistance at end of driving, whereas 233 is required using the ENR. If to retap the power, 197 kips is required as compared with 233 using the ENR, and the big difference is the construction method that you use. One is whip, one is ENR formula. Right? Step 10 basically is to cross-check and independent check on the design before the design and develop for the construction plan. So in the construction phase, right, what is required in whip and what is required in the ENR formula? All right? So in the whip, track 1, you perform the whip analysis, you prepare the bearing graph, whereas in track 2, you want to check the minimum and the maximum energy that's for selection of the right hammer to be used. Right? And you observe the construction. Both methods definitely require observation of the construction. There's no doubt about it. And you record the hammer blow counts. Both require that information. And you determine the driving resistance based on the driving data, the blow count and the stroke. And you determine the driving resistance from bearing graph, whereas in the ENR as a construction control, you determine that driving resistance using the ENR formula, right? And for example, in this, a contractor provides a Dalmac D19-42 as the hammer, all right? And you have the bearing graph, and you check the requirement of the hammer to satisfy the minimum and the maximum energy. And you record the driving blow counts as well as the hammer stroke. For example, at the end of driving, the hammer stroke is 7.5 feet. The driving resistance is 30 blows per foot are recorded. Using this information and under track 1, you determine that the driving resistance from the bearing graph is 88 tons, right, which is 176 kips. But what is required is 166. So since this is greater than the target driving resistance, we can say that the power performance is accepted, right? So we're happy with that. But how about if we were to use the same information and put it into this formula and determine the driving resistance, which is 191, but then we required a much higher target resistance, which is 233, and is still smaller than the target driving resistance. So if we were to use the ENR formula, that same power performance is not accepted. And the solution for that is to retap it the next day. Right? So if you to retap it the next day, you have, let's say, a hammer stroke of 8.5 feet and a driving resistance of 40 blows per foot are recorded. And for academic comparison, I still include that, although you do not need to calculate that, but just for comparison, based on this information, the driving resistance from bearing graph is 114 tons. Of course, it's greater than the required of 197 kips. Power performance is accepted. using the same information, put into this dynamic formulas, and now the driving resistance is 270 kips, and now is greater than the target driving resistance of 233. Only now the power performance is accepted using the ENR formula. Okay? So if you use the whip, at the end of driving, you're done with it, but this example shows that you require retap at 1 day. Hopefully it satisfies the performance if you use the ENR formula. Right? That's the big difference. So to summarize the comparison, both have the same numbers of powers, and the total contract length, as if you recall, 75 feet is required per power. In terms of 9 powers, total contract length is 675, whereas the 720 is required if you use ENR formula. The geotechnical resistance using the blue book is 197, whereas 213 is calculated. The target driving resistance at end of driving is 166, whereas 233 is required. If you to retap, the target resistance at 1 day is 197, a much higher target driving resistance of 233 if ENR formula is used. So what it means to you is that the power performance is likely to be accepted at end of driving if whip were to be used as a construction control, whereas relatively power performance is less likely to be accepted. So in other words, right, you have a lower chances of requiring a power retap if you would use whip, including the power setup in the calculation. In contrast, a higher chances of retap is required if you use ENR formula. Right? So to show you a comparison of the two methods, using whip and using ENR formula, hopefully you can get an idea of the two and make your own selections in the process of the design. So hopefully you can recognize the difference between the two methods, the outcome and the advantages of using whip with the setup component built into this formulation.